Yeah. All right. So we continue with stochastic dynamics of fields close to thermal equilibrium. Yesterday I was discussing Onsager's ideas on how to constrain the kinetic coefficients and then also constrain the corresponding noise amplitudes in a Langevin equation that describes these kind of dynamics close to thermal equilibrium. And today we will discuss gradient dynamics. This is relaxational dynamics close to equilibrium again. And Model A deals with non-conserved fields. And it's actually wrong here, sorry, it's for non-conserved fields. And Model B will deal with conserved fields. But let me go on the board and explain to you what I mean. So we have gradient dynamics. And this will deal with models that are called Model A and B. Model A is for non-conserved fields and Model B is for conserved fields. The approach that we take is one where we don't really start from macroscopic equations. We take a semi-phenomenological approach. And that means that we'll construct the theory based on phenomena we know and based on some general considerations. So what do? We assume, as we did in the last lecture, that the system can relax to a local equilibrium state, meaning at a scale that's large enough to coarse grain over microscopic degrees of freedom, but not macroscopic. We assume that this is a local thermal equilibrium. So that means we have detailed balance or time reversal invariance. And from that, we concluded the Onsager relations. Right, so in short, what we found is that the kinetic coefficients L alpha beta are positive definite matrices and that they obey certain symmetry relations that depend on the parity of the corresponding fields, and they are called reciprocity relations. Moreover, in shorthand, we found that n is 2LT or 0, depending on the parity of the coefficients, meaning there's a relation between the noise amplitude and the kinetic coefficients. Okay, what else do we assume in deriving the equations? We will rely on the symmetries of the problems, which is a standard way of approaching field theories by exploiting any kind of symmetry that you know about the system in writing down the corresponding field equations. And in addition to symmetries, we also account for conservation laws, so meaning, for example, that mass is conserved in the system. That's what I mean by conserved and non-conserved fields in Model A and in Model B. Typically, we will, in Model A and B, consider systems that are isothermal. That's not always the case. That's just here for the cases of Model A and Model B. And that means the corresponding object that we deal with is the free energy of the system. And you need to write down a theory for that free energy. All right, now let me show you how you can approach that. And for this, we first need to worry about what is that free energy that we consider as the basis for our dynamic theory. And that brings me to what is called Ginzburg-Landau theory. And there's various ways of motivating that. Let me remind you the case where we studied a system of Brownian particles, where I argued that you can use a macroscopic approach to derive equations of motion, but I also argued, based on very general grounds, that for a free energy functional, now let me write it in terms of a field phi, you can write this as two parts. One is an entropy part proportional to kBt of the form rho log rho minus, phi, that's what I mean, phi log phi minus 1. That's the entropy part of ideal gas. And then on top of that, you can have an interaction energy where you integrate over the densities phi of x, a pairwise potential between position x and y, and phi of y. Okay. That's such a functional where you locally assume that you can describe your system by a field. So phi is a real field, and x lives in d-dimensional space. It's a functional because it depends on the whole field as such. There is another way of arguing how you arrive at such a functional. It's by going to a classic, which I think you have seen, which is the Ising model. In the Ising model, the starting point is not a continuum. It's typically a lattice. And on that lattice, at each lattice point, you say you have a spin. The spin sigma I takes on discrete values plus or minus 1, and I indicate that here with closed and open circles. So something like that. This is one possible configuration of such spins on the lattice. And the way you can describe that is to say that I'm writing down a Hamiltonian, which is minus some kind of exchange interaction that you have between the spins. And then you sum over all pairwise spins and multiply sigma I with the value of the neighboring spin sigma j. That's not a field theory, that's a lattice model, and that you can study by various means in thermodynamics. What we want is a description here at the level of such a cell, which we indicate by x, and then smear it out again to have a continuous description, such that now I have a field phi of x that describes the configurations that you see in such a cell. And it's averaging over all the different spin configurations that you have. Okay? And as you have more and more of these spins in these domains, you can imagine that this ultimately leads to some kind of continuous description in terms of phi. There is a way of formally deriving from that a free energy functional But I'm not going to taking that route because this is a rare instance that this actually works out. Let's use symmetry arguments in order to derive what should be there. Well, this is a scalar field, phi, and this scalar field phi needs to have the same symmetries as the Ising model. So that means the free energy functional I write down has to have the parity symmetry of phi to minus phi. So the functions f of phi that I can write down here, these functions f of phi have to have the form of a Taylor expansion in even powers of phi. And let me call the coefficients, as is the custom in the field, as r over 2 and u over 4, plus higher order terms. And what I wrote down here are the non-trivial leading order terms that you can write down. That is not all, right? You can still have terms that contain gradients of the field. And these gradients also must reflect the symmetries of the problem, which is now translational invariance and rotational invariance. And that you can only achieve if you have an operator that does that. So we add here a gradient of phi squared and also write a coefficient in front of that to arrive then at this Ginzburg-Landau type of functional corresponding to the Ising model. And actually, if you take this one here, this field theory, and you assume that this potential is very short-ranged, such that the variations of the density are weak on the variation scale of the potential, you can Taylor expand what you have here, and you end up at a very similar functional as the one that you have here. Okay. All right, so that's my starting point for setting up dynamics. Now let's start with the first model that's usually called Model A, or to be more precise in terms of what it really is, it is relaxational dynamics of fields that are non-conserved, meaning that these fields can locally relax to equilibrium. And there's no conservation law constraining that. And actually not just one field, I'm looking at many fields, so a multi-component problem. So what do we have? We have fields phi alpha of x and t that are real. I consider R in a d-dimensional space, and alpha is running from 1 through n, where n is the number of components. So it's an n-component problem. The one-component problem is basically the Ising model that I wrote down. The higher order models have some other interpretations. So let's now ask of what can we write down for the relaxational dynamics of that field. Okay, so how do we argue? We argue that there are thermodynamic driving forces. These thermodynamic driving forces are the conjugate fields mu alpha corresponding to the densities phi alpha, the chemical potentials, if you like. And this is now in contrast to what we did yesterday, in general nonlinear relation that you can have between mu and the phi's. We looked at the lowest order linear relation. Here there's a functional derivative of our free energy functional, which can be of the form that I wrote down, that has arbitrary high order terms, in principle, of phi and gradients of phi. So I'm saying that this will be proportional to this chemical potential, so gradients in our free energy functionals. I need to put in front of that some coefficients, which are the Onsager coefficients. So this is then L alpha beta. And I want this to relax to thermodynamic equilibrium. So I better put a minus, and you later see that minus really needs to be there. Otherwise, the system would not relax to thermal equilibrium. These are the Onsager coefficients. And they need to be positive definite and obey the symmetry relations that we derived yesterday. Plus a noise term that depends on position as well. And for the noise, we take a Gaussian noise. That means the average of that noise is 0. And the correlation function for that noise is a white noise correlation function that is diagonal in the field indices. So we have delta alpha beta, short range in space, and short range in time. And the coefficients we call n alpha beta. Now the fields we have in mind, they are fields that all have the same parity. So you already know that you can relate the n and the L by the relation that we had, namely n is 2LT, and T is temperature. I show you another way of deriving that. So let me derive the fluctuation dissipation relation n equals 2LT via a Fokker-Planck equation. Okay, how does that work? You know that Langevin equations correspond to Fokker-Planck equation. There's a one-to-one relation. That's true for the simple models that we looked at before, but of course it's also true for these kind of fields. The difference is that instead of having sums on the right-hand side over the fields, you also do have then corresponding integrals. So the corresponding Fokker-Planck equation, which is a functional Fokker-Planck equation for the fields. Okay. So it's probability of observing this field at position x and time t. It's an integral over space. And then I have here, some convention. I have d over d phi alpha of x, and of course also t. And let me later on omit the argument. Then you have here the drift part, which is L alpha beta df d phi beta. Right, this is the drift part that we had before. times the probability functional. And we also have the part coming from the noise, which is n alpha beta d phi beta, the probability functional as a function of its argument. You've seen this. They write the same structure as we had before. Now, what do we know? We know that, because that's my constraint on the model, I want this to approach local thermodynamic equilibrium. And that means this Fokker-Planck equation must have the local Boltzmann distribution as a solution, as a stationary solution. So let's look at the stationary solution of the Fokker-Planck equation, which means that the time derivative is 0. Okay. And use P equal P equilibrium proportional to e to the minus beta times the functional f of phi. Okay, when you insert that here and you perform the corresponding derivatives, you get the f d phi. So the relation you find from that is 0 equals an integration over all space d phi alpha, then L alpha beta minus a half beta n alpha beta df d phi beta p equilibrium. Beta is one over kBt in the expression here in front. Well, and you're done, right? This then implies that n is 2LT as we had it. And KB in my notation is always equal to 1. Okay, so it's a very straightforward proof of the relation between the noise amplitude and the kinetic coefficients. And it doesn't go via the spectra. It just uses the one-to-one relation between Langevin equation and the corresponding Fokker-Planck equation. The next thing that we need to make sure is that free energy is actually the ground leading to a ground state, meaning the free energy is minimized by the dynamics. And this you can also express by saying that the free energy is a Lyapunov function. Let me show you what I mean by that. So let's take the derivative of our free energy functional with respect to time. And I would like to know, how does that evolve? Does it go to a minimum? And that's what I need. Otherwise, the free energy would not be a minimum would not be approached by the dynamics in a straightforward way. So that is, by the chain rule, an integral over space, the functional derivative of phi with respect to phi alpha, and then the time derivative of phi alpha. Okay, and now I can look at this equation here. In this equation, I have two terms. I have this one, and I have that one here, right? So if you insert this one, first term, you get integral d dx, and then with a minus sign, L alpha beta df d phi alpha times df d phi beta. So now let's say I want the typical behavior of that. Then I get rid of the noise term because that cancels out. And now, because this is positive definite by the assumption that we make on the theory, this has to be negative, meaning that the free energy is a Lyapunov function. It is monotonically decaying in time, such that as t goes to infinity, f of phi goes to a minimum, and this corresponds to the thermal equilibrium state. You can also turn things around. You can say, I didn't know yet what L alpha beta is in terms of being positive definite or not. Then you say, I want my system to have a minimum. That then implies that the L alpha beta has to be a positive definite matrix. And now I guess you also see why I have a minus here. If I wouldn't have a minus, this would all not work out. Okay, so let me recap this, because I think it's quite key. If you want to describe a local dynamics relaxing to thermal equilibrium for a field that's not conserved, you can write it as Onsager coefficients times the chemical potential plus noise. The Onsager coefficients have the usual properties. They obey the reciprocity relations, a positive definite matrix. The noise amplitude has to be related to the kinetic coefficients by this relation, 2LT. And then the system approaches the thermodynamic equilibrium state. You also see now, if you compare this expression here with the expression above, that the noise part, so this second term here, is key. If you don't have that, the system will not approach thermodynamic equilibrium, because I used that. I used the balance of those two terms to have the equilibrium state as the thermal equilibrium state. So the noise makes you reach the thermodynamic equilibrium state. Questions? Yeah?
Yes, so basically in this example, the noise has to be correlated between components alpha and beta if the L is such, for example.
Yeah. There has to be, the noise is given in terms of the kinetic coefficients, strictly.
Could it also be that, I don't know, if F is super bad or something, then we also have to get rid of the white noise assumption, such that there's also like a function of x and x prime, such that we relax to thermal equilibrium? Or that is
you don't have to have this white noise assumption to get the thermal equilibrium state. You just lose all the beauty of the math that we use. There will not be an obvious way to write down the Fokker-Planck equation, etc. So that doesn't mean these systems do not reach thermal equilibrium. It just means that you have been choosing a set of variables where there are some correlations left that you didn't account for. The usual logic is you try to set up a theory where all the slow variables are part of your theory. And only those that are fast, you then neglect or put in the noise. So think of a Brownian particle. You have this Brownian particle moving. That's the position. But you have all the water molecules surrounding it. and you ignore all the water molecules, and you say you can effectively describe that by a noise term in the Langevin equation. If there would be some correlations in the surrounding motion of the water molecules, of course, then the noise would not be white, and you would have corrections coming. And they would either show up in the way you have the noise, but then you need to derive the noise. You need to know what kind of noise it is and what the correlations actually are. Other questions? Good, then let me go to an example. And this is a scalar model A, so meaning the Ising model, basically, where phi is just a one-component real field. So in that case, there's no matrix. Your equation of motion simply is minus L df d phi plus theta. And the noise correlations are the same as I have them on the board. The on-site coefficient has a very simple condition. It needs to be positive. And now let's work out the equation of motion. So let's perform the corresponding functional derivative in the free energy functional. That is this functional here, for the case that I have this phi to the fourth potential. Then you get minus L, and then from a derivative of this term, this gives you R times phi. The functional derivative of this stiffness term that you have here gives you a minus Laplacian, so minus C nabla squared. And then you have from the derivative of the phi to the fourth term, the factor of 4 cancels. That's actually the reason why you choose 4 to be in the definition of this functional. So u phi squared, and this is all acting on phi. And then you have plus, let me add also an external field, h of x and t. And here, of course, as well, these are functions of the fields, of the coordinates, plus theta of x and t. So that's the dynamic equation that you have. And it's a not so trivial equation because it has this term here that's nonlinear in phi. It's a phi to the third term, and that makes solving this equation difficult. This equation has different names. I already called it Model A. It's also called the time-dependent Ginzburg-Landau model. Reason being, this is the Ginzburg-Landau free energy functional. This is the time-dependent version of it. And in the mathematical literature, it's also called the noisy Allen-Cahn equation, or just Allen-Cahn equation, where noisy means that we have a theta term, and without the noise it would be the Allen-Cahn equation. Okay, so it's difficult because the phi to the third term is the nonlinearity that you need to deal with. You can study that equation in various ways. You can say, let's approximate it, saying let's ignore this term here, or you say, well, I don't ignore it, but I have some means to account for that in a fashion that uses perturbation theory. That's all possible things, but maybe one thing I should note before we go on. If you look at the f of phi that we have there, then given that structure, you have different shapes. If this r is positive, then the parabola opens up to the top, and say the u is also positive, then this all just is basically a parabola. And that means if you are in that case, the r is positive, the ground state, the thermodynamic state of the system is one where phi is equal to 0. In the Ising model, this would be non-magnetic state. On the other hand, if you take r negative, then the potential looks like so. And the minima are here and there at phi plus minus being plus minus phi naught, which is the minimum of that potential. So now let me recap what I said. If you want to solve the dynamics of that equation, you can solve it in the high temperature phase, where you have a paramagnet, by looking around this minimum here and expanding around that minimum, and therefore neglecting the phi to the third term. Or you study them below the critical temperature, but then you have to expand around these respective minima that you find there, because they are the minima that you get in the end when the system settles down. Or you ask yourself, what happens as you cool down below Tc? What is the corresponding phenomena that happens? How does the system go from a non-magnetized state to a magnetized state? When you write at r equal to 0, and that corresponds to the critical point of the Ising model, then the way to approach that is using what's called renormalization group theory, and there you can actually really deal with the nonlinearity and discuss how the nonlinearity is affecting the critical behavior. I will not do this here. It's interesting, but it would sidetrack me quite a bit. Maybe I'll just show you for fun how things look like at criticality. So here, this is a state corresponding to a snapshot of a lattice gas model with black and white corresponding to up and down spins right at the critical temperature of an Ising model. And now what this simulation does, it zooms out. So this is a close-up view, and now you zoom out. What you should realize is it's always looking quite the same. And that's a characteristic feature of a critical state. At a critical state, the correlation length diverges, so there's scale invariance of the state right at criticality. So even when we do just Gaussian approximation, we'll see some interesting features of that critical state in our equations. Right, so the first thing I want to do with you is to look at Gaussian approximation for r greater than 0. Then the equation that we have is dt phi equals to minus L r minus c nabla squared phi plus L times H plus theta. This is a linear equation, and linear equations are solved by Fourier analysis. So let's do Fourier analysis and determine the normal modes. That means we now define the Fourier modes of the fields. Q is the wave vector, and this is defined as the spatial integral over a phase space factor e to the minus I q scalar product with position phi of x and t. When you do that, you transform this into a corresponding equation for phi of q and t. So the time evolution of the field in Fourier space is minus L r, and then the Nabla squared turns into a plus c q squared phi of q and t plus L h of q and t plus theta of q and t. And I also have for the noise correlation function that theta of q and t, theta of q prime and t prime is given by 2LT, 2 pi to the d, because I'm now writing out the delta function in d dimension for the wave vectors, times delta t minus t prime. And one thing you should also notice, because I'm doing a Fourier transform of a real field, phi of minus q and t is just the complex conjugate of phi and q and t. All right, so with that, before we go to a break, you can write our free energy functional also in terms of these Fourier modes. It's then a sum of Fourier modes. I mean a finite system, so this is a sum and not an integral. A half r plus c q squared, because of phi q and phi minus q related by complex conjugation. This is the absolute value of phi qt squared minus phi of minus qt. I don't need the t here, but let me just add it here. Okay. That is the functional that you have. And you can do the statistical mechanics of that. So let me not write the t here, I don't need this here. You can do the statistical mechanics by evaluating these Gaussian integrals, and as usual, you do this by calculating the generating function and then taking derivatives. Okay, and this generating function is, as we had it now several times, just simply evaluated because we do have Gaussian integrals in the harmonic approximation. So it's a half beta sum over q 1 over r plus c q squared, h of q, h of minus q. Okay. Correlation functions are derivatives with respect to h. So this gives you phi of q, phi of minus q, being t, because my kb is 1, over r plus c q squared. All right. Now, before we go into the break, let's visualize that. So as you plot this whole thing as a function of q, this has this Lorentzian shape. Okay, it's a Lorentzian. This has also a name. This is called the Ornstein-Zernike correlation function. And you can write it in a form which makes clear what happens close to the critical point. So Tc is at r equal to 0. At Tc, if you look at this expression, it will diverge when you go to wavelength equal to 0. So at Tc, this looks like a diverging function. And that's reminiscent of the correlation length because it's actually hidden in there. You can write that as a prefactor as q squared 1 plus q correlation length to the minus 2, where in our case the correlation length goes like r to the minus half, so like t minus tc to the minus half. So the correlations diverge right at the critical point. The correlation length that's described by this Fourier space correlation function is proportional to the inverse square of the distance from the critical point, and that's a critical exponent, which is actually a mean field or Gaussian exponent that's here coming out to be a half. This is modified by the phi to the third term. That means by the fluctuations. And this leads to a change that the actual beta is different from the mean field value by a certain amount, which you could calculate by RG. But qualitatively, even if you account for nonlinearities, you get the same kind of behavior close to the critical point. Divergent correlations at Tc. And that's what you saw in this illustration showing the zoom out of the spin configurations. Good. Let's stop here. Questions? Yeah.
What does it do with the Z? So it's an expectation value over what?
Which C?
The kind of partition function, I think, or the generating function.
Well, this C of H is the generating function. It's defined as so, as usual. Oh, sorry.
It's not that sort of partition function.
No, it's not a partition function. It is a generating function that I...
Like the moment generating.
Yeah, sorry, I messed it up here. This is phi of minus q, h of q. It's the moment generating function. That's something I have used in earlier parts of the lecture, which is in the case of a Gaussian distribution, the most straightforward way to actually calculate correlation functions. You could also just take the Gaussian distribution that you have here and evaluate the correlation function using that Gaussian distribution. Then you have to perform Gaussian integrals. That's also easy, straightforward. It's just much more straightforward, I think, to use the generating function for the moments, because you can calculate it from there by completing the square. And all that happens by completing the square is that you get the r plus cq squared from the numerator into the denominator.
And why does the moment generating function look like this? I know there's expect of e to the some parameter and then the random variable. Right?
No. This is here the generating field. Yeah, it's not a random variable. There's no random variable in these integrals.
And the phi would here be the random.
Yeah, here I want the correlation function. And if you look at this here, right, if you want the correlation function, you can get it by taking a derivative with respect to h.
Yes.
Okay. So I do this integral, which is here. So all I'm writing, because the average here is the average over that, right, over that part. That's the average I perform.
Over that part?
Over this part of the Gaussian distribution.
So you mean e to the minus f?
So let me write it down. Stop confusing you. The average is the integral over all d phi q's e to the minus beta over 2 r plus c q squared phi of q squared. That's my average. That's what I mean. This average here is written out, this average.
And then the inner part is what is left from the right of the Frey energy.
And this here is simply
This.
Yeah.
And then the z of h is kind of the normalization constant of this.
The c of h is defined as this. It's the generating function.
Yeah.
Give it a different name. I don't mean partition function here. It's a similar object. It helps me in a very straightforward fashion. Once I know the generating function, which is this one here, I just take the second derivative with respect to h. That pulls you down this factor here, and that leaves you with this correlation function for the external field set to 0.
What's the meaning of isothermal? I think initially you said for.
Okay, so what I mean is I'm using a system where temperature is actually really constant. There's no temperature variations in the problem that I study. There's no gradients in temperature. There's no gradient. There's no flux of any kind that would change temperature in our system. So temperature is time and space independent, a constant variable in the system. And therefore, the proper ensemble to use is one where I have the free energy. That's why. That's what I mean by isothermal. Maybe I should have better said temperature homogeneous in space and time. Good, let's break and come back in 15 minutes. That's at 25 or so.